In this exercise, we will try to use basic dimensional analysis. Let's consider a simple example. Let's say that we shoot a ball straight upwards, and we want to know the maximum height that it gets to. Now, I know that you can figure this out by using basic kinematics or energy considerations. In other words, you can find the expression for the maximum height from the laws of physics, starting from the basic principles. However, in this exercise, we will not use the physics laws, and we will try to find out what is the expression for the height and how it depends on some of the variables using dimensional analysis only. Now, in order to do that, let's first think about the parameters that could be involved here. So first of all, we have a ball, let's say of mass m. So mass m could be one of the parameters. There's an initial velocity v0, and let it just write without a vector. And then free fall acceleration g. And obviously the dependent variable h. Now, v0, m, and g we will call independent variables, and h in this example becomes the dependent variable. To start the dimensional analysis, we first need to write down dimensions of all these variables. So let's start with m. The dimension of mass m is capital M. v0, dimensions of v0, it's length per unit time, so L t to minus 1. Free fall acceleration g, that's length per time squared, so that's L t to minus 2. And h, dimensions is L. So that's the first step. You write down dimensions of all the variables, dependent and independent, that are involved in this example. Now note that we're not using any physics. We're just using the dimensional analysis. So the next step here is to make an assumption. You make an assumption of the functional dependence of h on other variables. So my assumption is as follows. I will say that height h depends on these three variables like this. So there is some kind of multiplication constant k, it's just a number. Then m to the power of alpha, v0 to power beta, and g, say, to power gamma. What are these constants equal to? At this point, we don't know. And this is where dimensional analysis can help us. If we say that this equation is correct, then it has to be homogeneous. In other words, dimensions on this side of the equation are the same as dimensions on this side of the equation. Dimension on this side of the equation, as you can see, is just L. K, as we said, is just a number, so it has no dimensions. We skip it. And then we have m to power alpha. We look at our table, so that's capital M to alpha. Then we have v0 to beta, so that becomes L beta, t to minus beta. And then we have g to gamma, so that becomes L gamma, t minus 2 gamma. And now, in order to find what are these alpha, beta, and gamma equal to, we need to compare the two sides of the equation. Now, you may say that on this side of the equation, we don't have m and t, but actually you do have it. It's just both of them are to the power of 0, whereas L is to the power of 1. So by comparing these two sides of the equation, we can make a system of linear equations. So what do? Let's look at m. We have m here and m here, which means that alpha is equal to 0. Then we have t here, here, and here, which means that minus beta minus 2 gamma equals 0. And then we have L. So L is here, here, and here. Which means that beta plus gamma equals 1. And this gives us a system of 3 linear equations and 3 unknowns. So we can solve it to find all the variables. Well, we already know that alpha is equal to 0. From this equation, we can see that beta is equal to minus 2 gamma. If we then use this and plug it into the last equation, we get minus 2 gamma plus gamma equals 1. So gamma is equal to minus 1, which means that beta is equal to 2. So now we have alpha, beta, and gamma. Let's now use these numbers and plug them into the original assumption for the functional form of h. So we get h equals k m to power alpha, that is 1, so mass is not part of this equation, v0 to power beta, g to power gamma minus 1, so g is in the denominator. So this is the result of the dimensional analysis. Now, if you remember the actual formula, you will recognize that this is the correct one. Now, you may ask, well, what do we do with this k? And the answer to that is that you can't find the multiplication constant using dimensional analysis because the answer given in this analysis is only up to this constant. To find it, however, you can do a series of experiments. So for example, if in addition to this analysis you perform an experiment or a series of experiments and you shoot the ball upwards with different initial velocities and then say make a graph of v0 squared over g versus h, you should get some data points. And if you do the experiment right, then you should get a more or less linear dependence. From the slope of this graph, you can find out the value of k. Now, you may also ask a question, well, if we can find this expression using the laws of physics, starting from the basic principles, then why do we need a dimensional analysis at all? And the answer to that is that you can get to a final analytical form of an equation if the problem is simple. But if the problem becomes more complex, then sometimes it is almost impossible to find the analytical form of the equation using just the laws of physics. And that's when the dimensional analysis becomes handy.